Today we're going to start talking about line integrals, and specifically of what are called scalar functions. So just to clarify, when you see something like this, say f of x comma y, this is a function of two variables that returns a single z value. When you have a function that returns a single value to you, no matter how many inputs it has, then that's referred to as a scalar function. Okay? And you've already had experiences with scalar functions in the 2D world. Anything you wrote like this, like f of x equals y, is a scalar function, a single variable. And if we think about integrating under these things, here's one of the ideas that we learned about. If we wanted to bring meaning to this expression, then we drew a picture. We drew what f of x looked like. So maybe it looks like this. And we named endpoints of an interval here, a to b. And then we found the area under that curve, or sort of the total, well, in this case it's the area because it's above the x-axis. But that was sort of the meaning we associated with this integral. You also considered things like this. For example, it was possible that the function you're integrating maybe went underneath the x-axis at some point, and if this was a and this was b, then you had some area above the x-axis, you had some more area below the x-axis, and then this expression, the integral from a to b of f of x dx, really numerically equaled the value of whatever this area was minus whatever area that was. Because area under the x-axis came back as something negative, the signed area that we were getting. Okay, so then that's just a quick review. So then the question is, what if we try and do what's called a line integral in a 3D world? And what does it look like conceptually, and what are we really talking about? Well, here's sort of the idea. The idea is, here's x and here's y, and here's z. And what you have is maybe you have a path. We'll make it a pretty simple path, and we'll call c in the xy plane. And what's going to happen is that path actually is going to become the base of our integral. Just like in the 2D world, the x-axis was the base of our integral, or the base of our area that we created underneath the curve. It's just that now our base is this curvy thing that I've called c. And somewhere above it, floating in space, is the scalar function f of x comma y. This is my poor attempt to draw this, but you have to imagine this is like a sheet holding up in space above the xy plane. And somewhere in that, on the surface there, if we were to trace up this endpoint and trace up this endpoint, then what we see on the surface, maybe something like that, on the surface of f of x comma y, is a curve whose shadow would be c in the xy plane, or the projection of which would be c in the xy plane. And what I want you to imagine now is what we're going to do is we're going to take we really want to find the area of this winky napkin, so to speak. Just like we found the area of the curve. Okay? The difference is that the base of this shape is not a straight line along the x-axis like it used to be, but instead it's curved C. Right, so now we're going to have a video of a video. Found a nice animation of this online. So what you're looking at here is a topographical map. The red areas are higher, and the blue and purple areas are lower. This is the x and y axis here. And what you're going to watch is an animation of a path through this. So I'll talk over this as we go. You'll see a path project onto this soon, and that's the path C. This is sort of the shadow of the path. And then this thing's going to rotate for us into 3D, and we can see now. So what you're seeing there, that blue thing that you're looking at, pause this for a minute, is the path on the surface that has the shadow that looks like this. Oh, hold on a second, let's bring it back. It's not letting me. Okay, so actually, here we go. You can see here, the red path is the path that's in the xy plane, and the blue path is the path that has that shadow. on the surface. So watch the rest of this, and you'll see there's the area and so forth. The red thing is acting like a curved x-axis, and now it's just going to snap straight. And when it snaps straight, there you go. It looks just like a traditional integral in the 2D world. Okay? And now you're going to see an expression underneath here, and we're going to have to make sense of that. Okay? All right, so let's take a look at how we can make sense of this thing. Well, don't forget that the curve C can be written as a vector function. So it might be written like this. R of t equals x of t I plus y of t j. Okay? Or like this if you like. Okay. So that's what you have. You have a parameterization for that curve. And for each point along C, there is a point up here on the surface. Okay? And we can get that because for each point along C, there's a particular value of t. Maybe we'll call this t1. And over here, there's another value, t equals t2. And for each of these values of t, we can get an x comma y on the curve. And once we had that x comma y, we could sub it into this scalar function and get the z value that goes with it. So this means that we can rewrite this path along here as a function of t by doing the following. We can say f of x of t, comma y of t. All right? And what's nice about this is that a single variable t now is giving me points along this green path. And while we're at it, let's denote a domain for t. Let's say that a is the lower bound for t and b is the upper bound for t. And that means that at this endpoint here, t is equal to the starting value a, and at this point over here, t is equal to the ending value b. All right. So now you can start to think about it. Well, all right, we want our line integral. We know it's going to go from a to b, and it's going to be with respect to t. Well, you want it to be that, and we'll get to that in a minute. And you also know the height of this rectangle is going to be x of t, y of t, or the height of the curve along the way. Now, I said rectangle. Let me sort of tell you what I'm thinking about that. Okay, so I'm going to take this picture and just redraw parts of it. So I'm going to draw another xy axis. Here it is. And here's z going up. And here's that curve C, like that. This is not exactly the same, but close enough. There's the scalar function, f of x comma y equals z above it. And then there's the green path above it, which is sort of the path on F that has C as a shadow or projection into the xy plane. All right? Now, when you first learned about integrals back in the 2D world, you used to do things like this. Before you even attempted to use fundamental theorem of calculus, your teacher talked to you about something called rectangle approximation methods. You ended up putting little rectangles underneath here. Okay? And this is sort of like the fundamental idea behind integrals, that you were adding up infinitely many rectangles that had really, really small widths. Each width of this rectangle is dx, and the height you get by doing f of x sub I, where x sub I is some kind of x value in this interval. And therefore, the area of your rectangles was f of x sub I, which is the height, times dx, which is the width. And then you added up all those different rectangles from A to B. And that's sort of the fundamental idea behind an integral. And you're really doing the same thing here. The same thing here you're doing is just that your rectangles now are along some curve C, and they sort of change, like a set of Venetian blinds maybe hanging, but they're hanging along a ceiling that's got a curved path up on the ceiling rather than nice and straight the way we're used to having them. Okay? So that has a consequence for us because we can't really say that the base of this thing is dt. That doesn't make any sense. That's not really what's happening. The length of these things are not changing time. A better name for these is ds, which means a small change in position along the parameterization. Okay? Now we should be careful. Our parameterizations here don't move backwards, so we're only going to move forwards along this curve. Okay? That'll make things much easier. We don't want to double count area here. Okay, so here we are. That's what you have. And what that means is our integral here, when we go to create a form for this integral, This dt at the end doesn't really represent the width. In reality, there should be a ds there. Okay, so our integral really looks like this. It looks like f of x comma y ds. The problem we have is that ds it's sort of special. You have to remember what ds is. ds is the length of the parameterization for small change in x and y. So we can actually find that by using Pythagorean theorem. We can say that this is equal to dx dt squared plus dy dt squared dt. And that is sort of the missing factor that needs to be here. So in here, you need to put this expression. And then you have, if you think about that all together, you have a line integral as a function of t. And it's probably worth, we'll do one example. All right, so let's do an example here. So let's consider a problem given to you like this. The line integral over a curve C of the scalar function 2 plus x squared y ds. So that ds is your clue that you're going to be moving along, not just an x-axis or y-axis, but some path defined by C. And we're also going to say C is equal to the upper half of x squared plus y squared equals 1. Okay, so we know we want to rewrite this thing in some kind of, in terms of t, where t represents the parameter in the parameterization of C. So if we think about x squared plus y squared equals 1, the upper half of it looks like that. We actually know how to parameterize that. We know that x of t can just be cosine of t, and y of t can just be sine of t. And that's what we learned is the parameterization for a circle. We need to restrict t, though, between 0 and pi. And the reason we're doing that is that sort of guarantees we only go halfway around it. This would correspond to t equals pi over here when we stop moving around the semicircle. And this would correspond to t equals 0 over here. Okay, so far so good. So now what we're going to do is we're going to take these things and remember what our line integral really looks like. The form of our line integral. There we go. I couldn't get the page to extend. Sorry about that. Looks like this. It's the integral f of x of t comma y of t d. Actually, let's be careful. And then it's going to be the square root of the x dt squared plus dy dt squared dt. I sort of picked a nice problem to start with. You'll see why in a minute. Sort of have to worry about this expression over here. This could sometimes get pretty nasty to look at. All right, so our integral now is going to go from 0 to pi instead, because those are the values of a and b that correspond to the beginning and end of the path we're moving on. And then f of x of t, y of t means you're going to take these parameterized things here, and you're going to sub them into there. That's what that means. So it's going to become 2 plus the cosine of t quantity squared times the sine of t. Okay? And then over here, this becomes the square root. Well, x prime of t, the derivative of the x component of this thing, is negative sine of t quantity squared plus the derivative of y of t would be cosine of t quantity squared dt. All right, so that's what we have. Let me get this board to align correctly. All right, well, some very nice things happen then, because if you look at this thing, this is really cosine squared plus sine squared, which is equal to 1, and the square root of that is 1. Yep, so that whole thing really disappears. This reduces to the integral of 2 plus cosine squared t sine t dt. Okay, so now we're ready to take our antiderivative. This looks just like what we used to do. You notice it looks like a scalar function of a single variable. And that's, in essence, what we've done by using this multiplication factor and subbing in the x of t and y of t here. We've made this to look like an integral that we used to do in single variable calculus. Okay, so the question is, what's the antiderivative? Well, the antiderivative of 2 is just 2t. And here, you should think of this like a chain rule in reverse. This is a cosine squared. I kind of like the way I wrote it up here better. So I know the original problem had to have a cosine t cubed in it. Now let's think about that for a minute. If we took the derivative of this right now, the derivative of cosine of t cubed, well, let's think about that. Cosine of t cubed call this the check here. The derivative of that would be 3 cosine of t squared times negative sine of t, or negative 3 cosine squared t sine t. So you know that this expression we have, this expression right here, is not really the antiderivative of that, because the coefficient's wrong. This has a coefficient here of 1, but this thing here, when you take the derivative, with a coefficient of negative 3. So what that tells us is there must have been a negative 1/3 in front of this. If there had been a negative 1/3, it would have canceled with the negative 3 that's down here. You can see how I'm sort of matching these up. And that's the true antiderivative. You can do that with U substitution also, but I don't think it's really necessary. Okay, so lastly, we'll evaluate this from 0 to pi. We plug pi in, we get 2 pi, and then the cosine of pi would be negative 1. Cubed would also be negative 1 times negative 1/3 would be positive 1/3. So that's what that piece turns out to be. And then if I plug in 0, 2 times 0 is 0. The cosine of 0 is 1. Cubed is 1. Times negative 1/3 is negative 1/3. Okay? So there you go, actually. Surprisingly nice. This ends up being 2 pi plus 2/3. And that's sort of the net area of whatever wavy napkin we've created by moving along this path, where the height above or below that path is determined by this function here. Okay, so there's maybe some kind of sheet coming up above it, and this is my poor attempt at a 3D picture. That thing's supposed to be coming out. I knew this was, actually this would have been 2, and that's really not that great of a picture. I know that would have been 2, because if x is 0 or y is 0, I get 2 plus 0. So it's going to be up to here and up to here. And then for these other values here, it actually gets slightly higher. So you have like some kind of semicircular fence that is 2 feet at the ends and higher in the middle. Okay, actually it's back to 0. It's back to 2 in the middle, interestingly enough. So it's like maybe higher out here and then comes back down, and higher out here and comes back down. All right, anyway, that's a brief introduction to line integrals of scalar functions. The key thing that you want to walk away with today is remembering this thing here that I've boxed for you. We've done an example of it. And remember the connection between that integral and this integral in the 2D world. It's really sort of a modification of what we already know. The next lesson coming up for this would be line integrals through vector fields, which is a different premise fundamentally. Thanks for watching.